Well, welcome everybody to CppCon, the final session of the first day of being back in person, which is really nice. Hopefully those of you who are going to be watching this online make it out here next year. It's a great experience. I'm Ruth. I'm a software engineer at Garmin, and I work a lot with legacy code, so I'm going to be talking about changing that legacy code with confidence, give you some practical advice for how to deal with this code without breaking things at work. So first, let's talk about legacy code. So the first thing that most people think of when they start thinking of legacy code and are faced with problems in legacy code is, we can start from scratch, we can rewrite this, and we can do a lot better than we could last time. But legacy code has value. It works. It's been out in the field, it's been doing what it's been doing for years, maybe even decades. It may not have tests in the unit test sense of the word, but it's been tested because it's been used for so long. The code itself is going to document all the decisions and problems and things that have come up throughout the years that code has been in use. And it's currently making the company money. So to go in and just to rewrite everything from scratch, you're taking something that is making the business work and you're betting that you can do it better and not make any mistakes. And another thing to keep in mind is, yes, there may be bugs in your code, but some people may rely on those bugs. Those might be really important features to some of your users, and when you go and fix them, it might actually make your users unhappy. Well, how does legacy code become legacy code? Like, people don't set out to make code that's hard to maintain or hard to use. Well, over time, best practices and languages change. The C++ that you were writing 10, 15 years ago is nowhere near the C++ you're writing today. And because of those new features, new best practices come into play. Developers are going to cycle in and out of projects, different styles, different philosophies, different ways of doing things. Features are going to be added, removed, re-added, changed, amended. All of those things are going to happen over time. New developers, when they come in, it's customary to say, hey, here's this small bug, go in and fix it. And they're not going to really have a firm grasp of the project structure or any of the underlying things that you're doing in the code. So they're going to mimic what they see to try and fix these bugs. And we don't write code just in a text editor. There's a bunch of tools, build systems and checkers of all types, fuzzers, things like that you put into your tool chain to make building the code easier. Well, those are going to change and migrate over time as well. So in this talk, we want to preserve working code. We want to get stuff tested. We want to introduce testing into the system. We want to gradually, over time, improve that code without negatively impacting the project that you're currently working on. We want to try and make this code self-documenting so that when people come in, they can understand what's going on. We want to instill confidence in making changes. So when you go into a section of code, you're not afraid to make a change because you'll have something behind you to verify that you didn't break it. And we want to develop for maintenance because we want the code we write today to be around, to become legacy code, to last decades so that people have to continue and update it because we want it to carry on. The cost of testing. So what you hear a lot of people say is, we don't have time to test. The code is not testable. We can't write tests for this code. We just have to get code out the door, and sorry, we just don't have time to do this. Well, whether or not you take the time to refactor your code, write an automated test, you need to test your code to make sure it works. So most of the time, that involves a manual process of compiling it and downloading it onto a device if you're an embedded system, or deploying it to a server and going through manual processes of clicking buttons to make sure that the code you wrote does what you thought it did. And if it doesn't, you have to go back and do it all manually again. So there's some testing strategies. I'm hoping this shows up well on the board. It does? Okay. So you can test everything on every feature. So here we've got a feature. It takes a certain amount of time to do. And let's say it takes a quarter of the amount of time to go through and test it. And every single time you do a feature, you go through and you test everything else. So by the time you get out to 8 features, you're spending more time testing than you are writing code. Well, no one's really going to do this. So most of the time what you get is you get the test the change you just made. And here you can see it's a significant savings in the amount of time that you're spending on the feature test cycle. But let's say you took double the amount of time to write every single feature with unit tests and craft it and put automated testing in there. And you can run those automated tests as you go through and add more features. As you can already see, after 8 features, it's a little bit less time than testing everything, but it's still significantly more than testing the change after we just made it. Let's say we write this last feature, and after we write that last feature, the test for the last feature passes, but we get a failure on one of the features a few revs back. Well, the search space for where that bug was introduced is going to be just that last feature we wrote. Not too bad, we can go back and fix it. Now, if we just did the test the change we just made, that last purple test passed. So everything that we did seemed to work. Time passes and a user reports a bug. Now all of a sudden, our search space is all of that, because we don't know exactly when it was broken. But if we write automated tests and run those things continuously, the unit test will fail on the commit that caused the failure. So you immediately know what code caused that failure and can fix it right away. Now, this graph might be a little bit skewed because, honestly, it can look like this. And that can be a significant amount of stuff that you have to look through and you have to debug and you have to try and figure out where this bug happened. So automated testing is going to reduce development time. It's going to reduce field defects. It's going to reduce the costs over the project lifetime. There are tons and tons of resources available. If you need data to back this up, to bring to people, academic papers, books, ways to go about doing things, just different philosophies, and recommend these if you have the time. But keep in mind, this requires determination. I'm assuming you're here because you have legacy code that doesn't have tests and is very difficult to test. So it's going to require some determination on your part to make this stuff happen. Code performance may be sacrificed. I know that C++ is always touting like this is a highly performant language, but in order to shift things around to make things more testable, more maintainable, more readable, it might sacrifice performance a little bit. And if it does, and performance is part of the acceptance requirements for the code you're doing, well, then you're going to have to do something to get that performance back. But for a lot of the code that you're going to have to manipulate, you can probably sacrifice a little bit of performance to make developers more efficient. You're going to fix other people's code. People are going to not create new tests for the code that they write. They'll just make sure that the old tests pass. You're going to own the changes that you make. So if you go in and you're the person who introduced testing in here, you are now the testing person. So when people have questions or issues or problems with testing, you're the person they're going to come to. Soft skills are going to be required. This is not purely a technical challenge because you're going to be working with other developers. You need to get people on board to start doing this with you and help you move forward. And everything is a judgment call. I'm going to give a bunch of different things throughout this talk that we're going to, ways you can go about doing things. But it's all going to be a judgment call based on what you currently have time for, what your current tasks are, what your goals are in refactoring. So keep that in mind. And this never ends. So just because you're spending all the time and doing it now, this is something you're going to have to keep up with over time. It's not a one and done thing. This is just a mindset change in how you deal with code. Can't we just use tools? I've been asked. Like there's automated refactoring tools, automated source tree tools, clang tidy format, debuggers, resharper, things like that all exist to help with tools. The problem with tools is not everyone's going to use them. There's some developers who have a completely tricked out system with all of the different tools and plugins and all these different configurations run on every single commit, but not everyone's going to do that. Some people are just writing in Notepad. Not all code's going to work with them. So the tools aren't necessarily going to support C++ 20, C++ 23 right out of the box. And if you start using that code's not going to work with the tools. They require maintenance too. So if you've got a build system and the build system upgrades and there's some changes to the version of Python it uses or whatever, these are things you need to maintain as well. They can be intrusive or leave artifacts in code. So like clang format, if you want to not format a section of code, there's comment artifacts to say, don't format this section of code. And as those tools change, you start seeing those comments in there that tend to end up having no meaning when you're not using those tools. Not all platforms can use all tools, and you need to understand what the tools are doing anyway, because the tool's not going to get it right 100% of the time. So when it gets it wrong, it's good to know what it was trying to do so that you can fix it. All right, getting started. This is one of the hardest things to do, is to just get motivated enough to do this. The thing I hear a lot is we need to add a test. But the thing I hear a lot is that, well, the code's not testable. It's not designed for testing. There's so many extra dependencies, external variables, C libraries, hardware dependencies, 1,000-line functions. I cannot test this code. Well, there are ways. So here is the first way. Hijack a function. So let's say we have a poorly designed page that has UI elements mixed with database elements, mixed with business logic, has some complicated initialization procedures behind it. To get this into a test harness is going to be a ton of work. And our goal is to add a new navigation feature where we want to go through and we want to, based on some filter, get the next item in a list. Well, we've got this onShow function here. And we know every single time this page is shown, it's going to call this function. Well, what if we were to hijack that function and put our test function inside there? And then we can use some type of dependency injection to pass in this pointer, to pass in a database, or any dependencies that we need to pass from our class into this test code. Okay, hopefully that's readable. So we have this getNextAsset function, and right at the top we're going to have a lambda that's basically just a simple cout, or you can print it to UART or whatever you want to do to say whether things pass or fail. And we've got a pass-fail, and then the line number that you want to use. All right, well now we can say we passed in the database clear, and we're going to run our first test. So we write our getNextAsset in list, and we're going to check to see if there's no assets, if there's an invalid ID. And now we get a little more complicated. We create an asset, add it to our database, and now we can test to make sure that the filtering's working and that it wraps around from beginning to end if you go to the next one. Getting even more complicated, we add in a whole bunch of cats, and we can now test to make sure that our dog and cat are all filter, work correctly, and over. And we've got this enable test, macro, to be able to just get rid of this when we're actually in production code. Now, you don't necessarily want to leave these tests in the hijack function, but it gives us the ability, because when we call that onShow, we know everything has to be set up appropriately, because otherwise the page couldn't use all of it. So we don't have to worry about all the extra dependencies, all the extra setup. We just use everything that would have existed anyway when our onShow function's called. Another good way of using this type of method is discovery testing. So sometimes you have this function, poorly named, bunch of interesting named variables that get passed to the function, and we don't necessarily know what it does or what we expect it to do. So find a place where it's used. So we've got this function, it calls it. Evidently at this point, the system is set up to be able to call this function. So let's comment it out, and then just start trying random things passing there and using our debugger, using some type of print output, using some method to kind of monitor it. We can start stepping through this code and start finding out, well, what is it actually doing with the code that we're passing it? And okay, now we've come to this activity bug, right? We've got a bug in our code where the distance that we're trying to determine between a start and an end location, it doesn't seem to be calculating correctly. So let's create an activity and pass it into our processing buffer. And in that processing buffer, we find this section with a bunch of 100-line functions, convoluted ways of determining the distance between two GPS coordinates. We've got some elevation calculation. We've got some incomprehensible code for calories burned. But ultimately, what ends up getting passed out is the amount of calories burned. We have no method of determining whether the calculation of the distance is correct. So what you can do is you can add a global. Add a global variable for the test distance, and where the distance is actually set, we can now spy on that distance. This is called the sensing variable in some of those books that I showed you. And then we can write a quick test that says, make sure that the distance from Tucson, Arizona, where I'm from, to the Gaylord Rockies is exactly 1,012 kilometers. Okay, so that's the down and dirty way of getting a test in there. It's not something that you're not going to be running it automatically. It's not something you want to have lingering around in code for a long time, but it's a way to get in there and verify that your code you're writing is doing what you expect it to do. So let's say you have a little bit more time. We're going to add a new main. So I work a lot in embedded devices, and we have desktop simulators for all of our devices. So if you've got some way of running your code on your desktop, there's going to be some method to hijack the main function that it's using. So I like creating some location in my project tests, and then you create a test package and a build manifest. You essentially make a complete copy of your simulator or whatever you're running on your development system. And you make just a separate extension of that to house your testing stuff. And I like adding a build flag for saying, hey, this is a test build, and they'll come in handy later. So we're going to enable that build flag and make sure we copy all of the flags that the simulator currently used. We're going to create a new build configuration, and at this point, you can build the product. And really all you ended up doing is rebuilding your simulator. And you can run it, make sure everything works just as the simulator did. But there's a reason that we use the simulator. It has all of the dependencies compiled in there already. You don't have to go through and try and pick and find dependencies and break dependencies throughout the code. It's all in there already. So you can start building up based on that. Now we can add our test framework, add that to the manifest, and set the appropriate configuration flags. Now, one of the flags that I point out here, this is just kind of the way that we set the flags, but is the Google Test entry point. So most test frameworks, Google Test, Catch2, stuff like that, have a way, they either define their own main or they allow you to define a separate main that you can then start off the tests. And that's going to come in handy because when we hijack the simulator's main, we're going to use that unit test build to conditionally compile out the main of the simulator. Now, there may be more things going on in that simulator, at the simulator's main, than just, kicking off the simulator. It may be some initialization that it's going to have to do, objects it needs to create, globals it needs to create. There may be some teardown stuff that you need to do. So, like Google Test has this test environment that gives you a setup and a teardown, which will give you the opportunity to do that stuff in your tests. And then kind of the boilerplate run all tests, and we're good to go. So now let's write our first test. This is basically just to make sure everything's compiling. So we got our first test, expect true, false, build it. I'm using WAF. It's a Python-based build system, but any build system will work. And go out and run our unit tests, and we have a failing test. Well, you can build off it from there. So now we've got everything in there, and as you start adding things to the tests, you've got all those dependencies so you don't have to worry about breaking them. But the best way to go about doing it is bottom-up testing. Because when you're doing that hijack main test, you're not really forced to refactor the code to make it so that you can insert dependencies and move code around and clean things up. You're relying on the existing framework. Ideally, you'd want to do a bottom-up test. So this is going to be your automated testing you're going to run every single time. So you want to start out the same way we did with the new main, create your build configuration, set your flag, add the test framework. But then we're going to have, in the files we're going to compile, we're going to have a separate testable and non-testable section. So every single time we have a translation unit, a C file, CPP file, that we want to start testing, we can start moving it up into this top section. And when it's up there, it's going to compile that code, but it's not going to compile everything else. So you'll have a very good delineation between what can be tested and what can't be. And then it's kind of, you get into this bottom-up testing workflow. So you're going to pick a function that you want to test, and you're gonna add a test. And then we're gonna just see if it compiles. So you move that file up in there, call that function, does it compile? Odds are it won't. At that point, you kind of gotta do whatever you can to make it to compile. So stub out functions, create local variable or create variables at the top of your test file, stub out dependencies, just do whatever you can to get it to compile. We'll deal with those things later. Once you get it to compile, now you need to get it to link. Same type of thing, stub things out, make sure that you can get everything to link, and then sometimes after it starts linking, you'll have more compile errors. That happens, but just keep repeating this loop. So once you get everything to link, then run it. Does it crash? Well, maybe you stub something out, set it to a null pointer, it needed to have a value in it. Keep going through there until it doesn't crash. So at this point, the file that you're testing is really messy looking and has a bunch of junk in it that you probably don't want to have there permanently. But we'll deal with that in a little bit. The next thing is to take a look at your tests. Make sure all tests meet your requirements. So that the point of writing this test, did you accomplish that point? If you did, now take a look at the tests. It's really common to just copy and paste a bunch of different tests to have the same preamble in the beginning before the tests happen. Refactor that to make it a little bit easier to read, a little bit easier to understand. And then this is kind of the judgment call portion. It's like, are you done? It depends on what your goals were. Okay. Next is going to be dealing with those dependencies. There are many, many, many ways to deal with dependencies. This is just going to be a few of them that I've dealt with over the past few years. So, yeah. All right. Easiest thing to do is just add them to the project. As long as they're pretty isolated, you don't want cascading dependencies. So a lot of times there's like a common utilities library or a common like header that a lot of the code in your company uses. Go ahead and add it in. It's pretty common that that's going to be used everywhere. But you also want to make sure that the dependencies are lightweight. You want to avoid having things that require, again, cascading dependencies or have long-running stuff like file access or network access that would make the unit tests not run very well. So one thing you can do with that is to create type-only headers. So over time, you start getting more and more things jammed into a header because they're needed somewhere. But if you actually sit and take a look at at the code you want to test, sometimes it just relies on one or two of those types. So something you can do is to just take the types that you need to define in isolation, move them into just a types file, because you don't need to have anything behind it, you're just defining a type. Include that in the code you want to test, and then modify the existing public header to just forward to the other one. So now you'll be able to include your enumeration that you have there without having to bring in all of the other dependencies that that other public header had, because you're not going to use them. Stub out what you need. So here we've got something that depends on the file system. So we're testing out our backlight timeout, and we want to be able to save the timeout time to non-volatile memory. Well, that requires the file system, which has disk drivers and maybe JSON parsers or whatever, but it's got this error code, data tag, and the write function that we actually care about. Well, create a separate file that's in a stubs directory. Don't actually include the file system HPP from the library. We're going to create just a small stubbed version that we're going to use in our library. And that is going to have just the error code, the data tag. It's going to mock out the ID to an integer, and just have a really simple way of reading and writing tags. Now, there's a catch with this, that this is not testing the actual code that goes into the file system. This is going to be some stubbed out version of it. But the idea here is kind of the same idea behind mocking, is that you're just getting enough information to mimic the way this code works. And you can hopefully depend on the existing file system stuff to work as it's supposed to. Isolating globals. A lot of legacy code likes to have just variables that are accessed everywhere. So instead of having getters and setters and things like that, it just uses extern variables. And in this one, it's a little bit more insidious because there are two definitions of that next window. And where that definition is actually made is dependent on some build flag. So as you're going through and trying to figure out, there's a bug in where this variable is set, there are all these different locations where the raw variable is used throughout all of the different code here. So write getters and setters. So getters and setters are going to first find the common code that everything is going to use. So something's going to be compiled in every build configuration, and you would define it there. Create a getter and setter that simply just returns your next window. What that's going to do is it's going to limit, it's going to create a choke point. So all of the different ways that someone can set it, they're going to be able to, they're going to have to set it through this function. So it's going to be greppable. It's going to be something you can search for. So instead of just searching for the variable, which is just going to be everywhere the variable is mentioned, and it's going to allow a place where you can put a breakpoint or put print statements or something to that effect so that you can reason about it better. Testing with time. So this is something that we run into a lot is, well, I have something that's very timing critical and timing dependent. How do I write a test that goes and mimics that? Because it's critical on the way the time works. And I'm using some low-level, operating system or custom-built real-time clock that uses a bunch of C code with git tick. Well, here we've got a backlight manager, and it's got a background thread that just keeps getting the time, and after a certain amount of time of the backlight being on, it wants to make sure that that backlight turns off, right? And they got calls to got tick right in there. So if we could modify this, we could go in and just make a separate, get time function, and then for our tests, we can just override it. But for the sake of argument, let's just say we cannot change this backlight manager. This is not code that we're allowed to touch. So how do we test the time? Well, the first thing we can do is create a new testing header. And we need to have the extern C there because that's a C API, so we need to make sure that the linking for the git tick that we're going to be implementing in our CPP file is linked appropriately because other code may require it to be non-mangled. And then we create a new test CPP file that includes our header, and we also have our test, all caps, _ set tick. I like capitalizing test in front of it, so if you ever see that in production code, somebody's using some code they shouldn't. But all it really is going to do is have a time in the background, and we can set and get it. Then you can utilize your unit test build flag. So in this build system, we say, hey, if we're doing a unit test, we want to link against the dummy test version of our timer. Otherwise, if we're not doing a test build, just link against the existing C API that we're using. And then that allows us to do this. So we have a start time. We're going to set our tick to our start time. We're going to create our backlight manager, BLM, and we're going to say after 1 hour of the backlight being on, I want it to turn off. We turn the backlight on. We increase our time by just under an hour. Make sure that it's off. Make sure that's still on. Increase our time so it goes just over an hour. Set the time, and it should be off. And if there's a little bit of delay on there, you can, since this is running on a separate thread, you can throw a little sleep of a few hundred milliseconds or whatever. But the idea here is we don't have to wait the hour to make sure that the backlight turned off appropriately. The scout rule. This has been worded many different ways, but as far as I can tell, this is the original way it was worded. Try and leave the world a little bit better than you found it. And this is more geared towards campsites and trails and stuff, but it's appeared over and over and over again in programming. First, a note on refactoring. Do not refactor and add new functionality at the same time. It is very easy to get into that trap and spend hours and hours and hours going through code and, oh, I can just go and fix that, and oh, that needs to be moved around. And you look up at the end of the day and you go to make your commit, and there's 30 files changed, and there's no way to tell what's the new code, what did I modify, what really happened here. Not only is it going to make it hard for you to see what's going on, but if you do code reviews, which you should, the reviewer is not going to have any idea what they're going to be looking at. Always commit working code, even if it's not the final stuff you want. Most of us nowadays are using Git or some type of version control system that allows you to commit things locally. Take advantage of that. Anytime you make a change that compiles, or you make a change that you like, or you want to start going into a different direction, make a commit. There's no pain in doing that locally. Make one change per commit. Again, this is going to be something that's just going to make it easier to see what's going on with the code versus having to kind of split out multiple things in your commits. And give yourself a time limit. It's very easy, again, to just get lost in the code. And Slack has an awesome feature where you can remind yourself after a certain amount of time to stop doing something. Or you can set your watch to give you a time limit. But by giving yourself a time limit, you're going to make sure that you keep your mind on the task that you're actually supposed to be doing, which is developing this new feature or fixing this bug, and not spending time refactoring and moving code around. At the end of your time limit, create a new branch locally, commit this code, and you can come back to it later. New code should be tested. As you're writing new code, make sure you have a test around it. You can use something like sprouting functions or sprouting classes, where instead of writing the code inside the function or inside the class that you're actually using, you can create a separate class, write all of your tests in isolation, create this code in isolation, and then integrate that as a member into the class or as a function called from a larger function. That way you can start moving more and more stuff to testable code, and you're not contributing more and more to the bloat of the existing stuff. Data accessors. There is a CPP core guideline to avoid trivial getters and setters. Now, there's a note in there that basically says trivial is up to the user. Another one of those it depends type answers. So we have a data only struct. It's a position with a lat and longitude. That is a perfect example of something that, you don't necessarily need to have getters and setters. You could have getters and setters to verify that they're valid latitudes and longitudes, but for the most part, you're just going to be passing this around as a data only struct. That's fine. Nothing wrong with that. If I saw it in a code review, I'd let it go. But then you build on that over time. So now we've got a packet for geofencing, and that's going to have a GPS type in there. But again, it's a packet. It's just public data. There's no need to have a bunch of complicated functions or things like that. Well, now we've got this. And then this packet is now part of a weather packet. It's another packet. It's going to have just public data. There may not be anything we need to really check on that. It's just passing around a struct. And the previous person who wrote this geo packet just created a struct as well, so why should I create a struct here? And then over time, there's now a differentiation between the geo packet and the weather request. So now there's an embedded struct in there. And then that starts ballooning to now we want to support all of these things over a satellite payload. So we have a union of all of these different structs, and all of these things are public, and it leads to code like this, where you have a payload, whether request geoposition, .long, and .lat. And that's just hard to reason about, hard to deal with, and when you're trying to figure out where the latitude and longitude are changed, there are a lot of places you might run into it. So take the time, as you're adding in this code, to think, at what level is this starting to get out of control? Maybe I could have refactored when I had that request and said, hey, getters and setters would be nice because now we can make a geo request and a set position and a set request geo. And by having this code in there, that person who hasn't seen this before and you want them to go in and add a different type of request, well, now they see this code and they see that, oh, I need to derive from a request and make a new request and pass it in there. So by example, you are making the default be the better code. Remember that extern isolation before? Well, we said before, it's a single definition. So now we have one place we can look for everything. It's going to prevent accidental change when you're reading that variable. The whole double equals versus equals thing. You're going to have the ability to add diagnostics to that code. So anytime that's changed. So if you don't have something that has a data point or a data breakpoint when data's changed, like maybe you only have UART output, or maybe you don't even have that. Now you can add diagnostics to the code. You're going to reduce the locations where it's changed, so you're going to kind of limit the scope of where you have to look. You'll have the ability to override. And it's going to prevent proliferation to other files. So if somebody sees you using an extern all over the place, and they need to add a new file, you can bet they're just going to use the extern that's been used everywhere else. And this is just kind of an aside real quick. Adding call site diagnostics. So again, you're not always going to have a debugger hooked up or a debugger that works with your system or a license for the debugger in some cases. So if you can use C++ 20, you're in luck because they added the source location. And all you need to do is if we want to see all of the call sites for this pairing view model, so like maybe there's a bug where this is being called and there's a crash, and you just want to know which of the many different ways to get to this function does this crash actually happen. So update pairing state is going to be called throughout all of your code. If you modify the actual function and just add a default argument with the source location current, and then in your backing file, we take that source location and we print out the file name and line and everything. You can leave all of your other call sites alone. You've got to recompile and relink, but you can leave all your other call sites alone. And that source location current actually grabs the current file function line number of the call site of where it's being called. So you can track where it's going. And for those of you who can't use C++20, there is a little hack you can use with macros. So this is going to require you to change the name of the actual function. So here we've got to change it to update pairing state temp. And we create a separate function that's update pairing state log, which is going to take your whatever functionality you need to forward, and it's going to return whatever functionality you need to return. And it's going to take the file and the line number. And we're going to print that out, and then we're going to forward it on to the actual underlying function. And then we're going to have a macro that's going to replace all of the call sites with that update pairing state log state file line. Now you might wonder why have the macro with that, why not just have a file line as default arguments to that function like we did with the previous one? It's because the file and line macros are going to use the file and line of where they are. So you will get the definition site of the function, not the call site. So having the macro makes it so that the call site gets the line and file number. Use public functions, even in private. How am I doing on time? Oh, great. Okay. So we have this VHF device. It's going to have some member functions, and throughout the life of this code, more and more code is going to be using this update rate. And it's going to be checked and set and read all over this CPP file. And the more code that does it, the harder it is to know where this individual variable is being changed, where it's being read. And even a harder thing about this is we have these public functions. So these public functions that we have for getting and setting and checking to see if it's asleep, they're going to be the ones used by people who are using this class. So we might have some things in there to make sure that the update rate is a valid update rate, or that it doesn't go over a certain threshold in certain instances. And if somebody's going to come in and add that functionality, they're going to add it in the get update rate. They're going to add it in the set update rate. They're not going to go through and find every single instance of m current update rate, or they might not catch all of the uses of m current update rate. So there's going to be some instances where it's set and it's missed. But if we go and we replace all of that direct access for those members with the public functions, we're now creating another choke point where all of the changes, all of the sets, everything is going to funnel through these functions. And any maintenance, any bug fixes, anything that's done to these public functions, we can automatically take advantage of in our private member code. So what does this gain us? Well, again, you get a single path for all internal and external callers. So it's easier to test, easier to reason about the code. You're dog fooding, or you're actually testing out the usability of your public API. You know, sometimes as you go and try and do this, you'll realize there's things that you want to do that you can't do, and then you can ask yourself, is this something that the users of this class would want to do? All the changes to logic occur in one location, and again, the ability to override for testing. Ease cognitive burden. Ugh. As somebody who maintains code for a living, reading code is very difficult. And figuring out what code does, while possible, is maybe you spend more time reading code than you do actually writing code. So you want to make it, when someone's reading your code, that they don't have to think that much. So you've got this giant function, and you think your bug's in here somewhere. And you notice that it takes this packet in here by reference. So we need to find out somewhere in this giant function where this packet's being modified. And we see these functions kind of a select few of them that are taking this packet as an argument. Well, let's make that packet const and just see what happens. Well, the first two failed, but the last one compiles. So as we're looking through and reading this function, any calls to set notification, we can just ignore those because it's already const and it's not going to be modified in that packet. So let's dig in a little bit to those other two functions and let's make those const. Well, it looks like the calculate bark rate passed. So we don't have to worry about that anymore. So we can focus in on that validate packet because that seems to actually modify the packet. So we remove the const packet, and now we can dig into that validate packet function to see what's going on. And wow, it looks like this was brought forward from C code because everything's declared at the top and not initialized. So the first thing we're going to do is we're going to reduce scope and const things. So let's find the first location of where all these are located, add some autos in there to make life easier, const everything out, and then compile it. All right, it looks like the bark count is actually going to be modified at some point. So now we could ignore those other variables that we const out. So again, we've decreased the amount of cognitive burden to find out where things are being modified. Because once something is const, it's const. It's not going to be changed. So we can go back, change that back, and now we know what we're looking for. Document understanding. So you spend time going through this code, and you need to figure it out. So for this particular set of code, I'm adding a point to a course. And the second variable there is a track point count. And I see it used there compared to 0, see it used there compared to greater than 0. Well, track point count, that doesn't seem like what it's doing. So after spending some time working with it, testing it out, see what's going on, you realize all that code is actually telling you is whether I need to reset my distance calculation or accumulate to the existing distance calculation. Well, now that you know what that code does, take the time to go in there and make it so the next person who has to look at this code doesn't spend half the day wondering why when they pass a track point count of 72 that the 72nd track point doesn't get set. This type of code is more extensible. It doesn't really add much overhead to what's going on, and you're documenting what's going on so people don't have to figure it out again. Everyone's favorite acronym. Prevent maintenance resource bugs. So this is actually a correct function. We reserve our mutex, we release our mutex, and return early, or we release our mutex later. So it's correct. But if you've got the time, make it so that the next person who may add something to this function won't accidentally forget to release it. By doing this, you're ensuring that under maintenance, anybody who's going to modify this is not going to have to concern themselves with it. So you're preemptively preventing a bug with very little extra work. And over time, you can actually move this into some common header, and then everybody might start using it. Because when they find they don't have any deadlocks because of this, they might be happy. Recognize algorithms. So here, it is file in files to keep. We pass in a path. We've got some files to keep list. You can figure out that that's what this is doing, is finding what's going on and breaking and returning from it. I mean, it's not too bad. But if you have something like a find if in there, yeah, the code might be a little more characters and a little bit more to process, but having that find if in there immediately tells the person who's reading this code, this is a find. This is what's going on. Because you can't always trust the name of a function to actually do what it says it does. Boolean arguments. So this is going to have a Boolean argument for is activity, right? Whether activity is true or false. But we don't know what the false is, right? Okay, if it's true, it's an activity, but what is not an activity? So once you figure that out, you can now switch it over, again, to an enum. I'm a big proponent of switching things to enums when there's a finite number of things. Like Booleans, true and false, those are more conditions, not arguments. But a nice thing about having this is now, if somebody needs to add a new type, they can just add it in there. And it isn't going to affect the existing logic. So if you have that Boolean in there, throughout all of the code where it's checking to see if the Boolean is true or false and doing different things based on that condition, if you add a third thing that's another Boolean in there, well, that's going to require a lot more finessing of the code on the back end. And even all of the spots that use that Boolean may have to be touched. Or if later on you convert it to an enumeration, like maybe it's going to require a lot more work. But by doing this, places that don't care about this new track aren't going to have to be touched, because an enumeration can just keep getting extended, and only the new stuff that need to worry about these new things need to actually handle it. I love this quote by Martin Fowler. Any fool can write code that a computer can understand. Good programmers write code that humans can understand. And that's really the point of all of this, is because just because the code works on, you don't want to write once code. You want to be able to maintain this code and modify this code and bring everything forward over time. You want more people to contribute to this code. You want to be proud of what you're writing. And the easiest way to do that is just tell a story with your code. To be able to have it be a narrative that someone can read and understand what's going on and understand what the program's trying to do. You're not just telling the computer to convert words to bits. So, to sum up, take the time to write code for maintainability. It's going to help your company move quicker in the long run. It's going to ease the cognitive burden of people who have to maintain the code, even if it's yourself sometime in the future. And you need to lead by example, because, like I said, this is a lot of work. And the better example you can set in the code, the more new people who come into the code, they'll be able to see a better way forward and not just keep propagating the legaciness of the code. So with that, any questions? Oh, I know it's the last session, so.
Thanks for the talk. So you talked a lot about adding tests to legacy code. Do you have any strategies for making it so that those tests don't then stop you from doing other refactorings, because now you have a large number of tests that are inserted in various locations and rely on various esoteric setups?
So it's not a long-term solution. Like, the point of having those like hijack a function tests isn't necessarily to make a long-term solution for testing. The point of that is to make sure that the code that you are writing is doing what it's supposed to do. Like, that is a stopgap solution. So that's one of those things where you absolutely have to get something done, like you don't have time to do any refactoring, or it's a monster refactor, and you just really want to verify what you're doing is correct, or you want to figure out what's actually going on. So I do not recommend keeping those in as a long-term solution. It's just a stepping stone to get started down that path.
So then what's the goal to progress after that?
The goal to progress after that is to start doing the refactoring, to start moving things out. So like, break out that section into a separate function, make that function testable. So this is the answer to this is not testable. Like, everything is testable.
Thank you for the talk. Talking about these big legacy systems, what is your take on the integration tests? Because you were mostly talking about unit tests. I can provide example. So the kind of integration tests where you control and can feed the specific looking like real input to the system and record the result. And later on, you probably can modify it, refactor it, and compare if the results stay the same on changes. Mm-hmm.
Yeah, so we actually have, I work with VHF communication between different devices. So to test communication between VHF devices is kind of a difficult thing to do in like unit test frameworks and stuff. So what we ended up writing is we ended up making just like a little dummy system that has code on it that we can then use for that type of logging and comparison stuff. So we can do real things back and forth and send commands back and forth over VHF using this little dummy system. So it's a separate little hardware thing you can write. You can do the same thing with servers. You can make a little separate dummy server that sends those and feeds things back and forth. So did that answer your question, or?
Yeah, but do you think it's useful technique?
Yes, it's 100% useful because, especially now with the chip shortages, it's very hard to get all of those things for embedded devices. So having something where you can mimic a device and not have to spin a whole bunch of boards to give out to people to test. If you just have a little thing on your system where you can just load the software up and mimic it, you can actually have the software start progressing before the hardware is actually completed. So those things are super useful for that type of stuff.
Thanks.
Yep.
When you're adding new tests to legacy code, and naturally when you write new code with a test-driven development approach, it's easy to come up with the test to write because it's the features you want. Can you share some strategy on figuring out what to even test in the legacy code when, yeah, it works for now, so what do I even start to try to test?
Whatever you're working on. So kind of the example there is you need to go in and add a new set of functionality. That's a perfect opportunity to go in and test. If you're trying to do some verification, so we were trying to verify that some codes that we use to exchange frequency information were correct. So we started doing that type of testing on there to kind of suss out, okay, this is the code that the customer sent, this is the code that the customer got, that's not correct. So I'm gonna take that real world bug that the customer reported and just drop it into a test and replicate their bug and then work from there. And I left that test in because this is a real world scenario, it's a bug that we had to fix, I took the time to write the test. So now that customer's problem is a permanent automated test. So yeah, again, it's up to you as to what you want to start at. What I would not recommend doing is I would not recommend sitting down and being like, I'm going to start converting everything to tests, because you'll end up digging yourself in a hole, and I've many times seen that methodology get abandoned and people just go back to the old way.
Thank you.
Yep. A little closer.
If my legacy code is a C code, non-object oriented, now I want to refactor to a C++ with object oriented design. Could that be difficult or doable? How doable?
It's definitely doable. In fact, one methodology that we go about doing, and this is something you can do for providing public libraries as well, is you keep your C interface for the header. So just all the individual functions and stuff like that. And then on the back end, you create, instead of a C file, you create a CPP file. And you start building your class and your struct, or your class and all of the functions at the top of that CPP, or you can have it in a separate header or whatever, but you start building that in the back end. And you just basically provide this thin layer between the C API and your C++ API. And if you need to forward pointers back and forth, pointers, as long as you're not operating on them in the C environment, if you pass, if you give a void star pointer out and they pass that void star pointer back in, you can cast it back and forth internally to your code, have some mechanism to determine what that handle is. But that allows the C code to continue calling the exact same functions, and then you can gradually build up the object-oriented on the back end.
Okay.
Okay, there's no other questions. You're free to go 6 minutes early.